So in this video of chapter number 13, which is surface areas and volumes, we are going to start with another solid three-dimensional figure. It's called right circular cylinder. So let's see what is right circular cylinder. Now key point to remember is that this is a three-dimensional, okay, or a solid figure. So we did see in the previous video that what is the meaning of these three-dimensional figures, or sorry, solid figures. Basically these are not your two-dimensional figures, okay, like the circle or a rectangle or a square. Okay, these are three dimensionals. Basically they are made from two-dimensional figures itself by doing vertical stacking or vertical piling. So I'll just note down the keyword. It's called vertical piling, okay, or you can also call it vertical stacking. Okay, vertical stacking. If you do a vertical stacking of such two-dimensional figures, you get three-dimensional figures. So now the focus is on right circular cylinder. Let's see how right circular cylinder comes into the form. Now let's get rid of this. Okay, so here you can see one simple, okay, I'll try to zoom in. Yeah, so here you can see a simple circular, let's say a piece of paper here, and if you keep on stacking many such circular papers, one above the other, one above the other, one above the other, eventually what you end up getting is something called as a right circular cylinder. Okay, that is a very simple definition, or a simple understanding, simple concept of how a right circular cylinder is formed. Okay, the key word here is, as we have seen in the previous video, the key word is vertical piling or vertical stack. Whenever you take any two-dimensional figure, okay, and create a stack of it one above the other, pile it one above the other, what you end up getting is a three-dimensional figure. Okay, so previously we saw two important figures. One was cuboid and one was cube. Okay, and now you are guessing right circular cylinder. So this is a simple concept of how a right circular cylinder comes into the picture. Now the key thing that we want to understand in this lecture is the surface area, curved surface area of right circular cylinder. So first of all, let's get rid of this. So first thing that we are going to see is the curved surface area of a RCC. RCC is nothing but right circular cylinder. Okay, so let's draw a right circular cylinder. It will look something like this. So we're going to have a circle, okay, at the base, and then we are going to have two straight lines like this, okay, and then we are going to have another, sorry, two straight lines like this, and then we are going to have one more circle here at the top. Okay, so this is how your RCC or right circular cylinder looks. Now what is a curved surface area? So let me use a highlighter. Curved surface area is this, okay, this surface area, okay, this surface area of the cylinder. Okay, basically curved surface area of any three-dimensional figure is the area excluding, okay, let me erase this highlighted part. So we have to exclude the roof and the base. So in this figure, this is our base, okay, this whole circle is our base, and this is our roof. Okay, if you exclude this, if you remove this from the three-dimensional figure, then whatever remains is called as a curved surface area. Okay, so for a right circular cylinder, the curved surface area is going to be this perimeter. Okay, so okay. So this perimeter of the circle, okay, what is the perimeter of the circle? So let me make a note of this. The perimeter, or it is in fact called the circumference, perimeter or slash circumference of a circle, just of a circle, okay, is equal to 2 pi r. Okay, this is standard formula, we all know. So if you just come here, yes, so this perimeter of one single circular disc is equal to 2 pi r. And now how are we constructing a right circular cylinder? We are taking this one circle and then going above till the height h. Okay, so this is 2 pi r. Once again, okay, this is 2 pi r. Okay, and if you multiply it by this height h, then we'll get the curved surface area of RCC. Okay, so I'm just going to write it down. Therefore curved, okay, surface area of RCC, right, circular cylinder, is nothing but 2 pi RH. Okay, let me write it in a better way. Is equal to 2 pi r, okay, multiplied by h, and let us box it. This is an important formula which we'll be using in solving many unsolved problems. Okay, now once we have seen this, the curved surface area of RCC, the next thing that we are supposed to see is the total surface area. So let's get rid of this. Okay, so what we are going to see next is total uh, total surface area of right circular cylinder. So once again, I'm going to quickly draw a right circular cylinder here. So this is the roof. Okay, so a circular disc, and that these are the two straight lines, and another circular disc. Okay, this is how a typically right circular cylinder looks. Now, what is total surface area? Total surface area includes this whole curved surface area. Okay, this whole curved surface area plus the roof and the base. Okay, all the things included gives us the total surface area. So now we very well know that the area of this upper roof, which is nothing but a circle, is equal to pi r square. So I'm just going to make a note of that. So this we all know is equal to pi r square, which is nothing but the area of the circle. Similarly, let's use the same highlighter. This thing is also going to be pi r square h. The roof and this base both are going to be pi r square in their area. Okay, and if you exclude this roof and the base, then what remains is this figure. Okay, this figure where we already calculated the curved surface area, which is equal to 2 pi RH. So what is the total surface area of RCC? The total surface area of RCC is going to be equal to pi r square, which is our roof, plus pi r square, which is our base, and plus 2 pi RH. Okay, this 2 pi RH comes from this one. Okay, it is nothing but the curved surface area. Okay, this curved surface area of the cylinder, this thing. Okay. So now let us try to write it in a better way. So this is nothing but 2 pi r square plus 2 pi r h. So 2 pi r is common, so I'll just write here like this, 2 pi r, and it will be r plus h. And this is another important formula. I'm going to box it. For the total curved surface area, or the total surface area of RCC. Whenever they're asking us the total surface area of any three-dimensional figure, not just right circular cylinder, we have to add all the possible areas of the figure. So which basically includes this roof and the base and even this curved surface areas. However, when the word total is not there, okay, so what we have is just like this curved surface area. Whenever they're asking you curved surface area of any geometrical figure, we exclude the roof and we exclude the base. Okay, and whatever remains, you just find out that area. So try to understand the concept. The concept is very important because there are different geometrical three-dimensional figures in this entire chapter. We have cube and cuboids and cylinders and cones. So in order to spheres, so there is no point in just by hearting the formulas. We have to understand the concept. What is curved surface area? What is total curved surface area? And then depending on the problem and depending on the geometrical figure that we're trying to solve, we have to apply the formulas. So that's all. This is just a conceptual introduction of what exactly is RCC. We saw what is RCC, and then we saw what are its curved surface area and total surface areas.